Welcome to the deep dive. You know, we often see these massive structures around us, bridges, skyscrapers, even the frame of your car, and they look so solid, so unmoving. But have you ever stopped to wonder what's really happening inside their very molecular structure, especially when they've been fused together with intense heat? Today, we're taking a deep dive into an unseen battle that plays out in almost every piece of metal joined by welding. Residual stresses and distortions. It might sound technical, but these invisible forces are absolutely critical to the safety and longevity of practically everything we rely on.
That's exactly right. This deep dive is all about unraveling those hidden forces. Think of it as a constant internal tug-of-war within the material, one that can subtly, or sometimes quite dramatically, twist and stress the final product. Understanding this isn't just for engineers, it's, well, fundamental to appreciating the incredible complexity behind what appears to be simple metal joining.
And that's our mission today. We're going to unpack what these residual stresses and distortions actually are, explore how they develop from the very moment the weld cools. We'll examine their real-world impact, because this isn't just academic, right? It's about preventing catastrophic failures and, most importantly, discover the ingenious ways engineers and fabricators battle them. Through clever design, smart assembly, and even post-welding correctional techniques. Okay, let's unpack this hidden world. So let's go right back to the beginning. When you apply that intense localized heat during welding, it's obviously melting and fusing metal. But what's the immediate effect on the surrounding, the still solid material?
Well, the moment you introduce that localized heat, the metal right around the weld area, what we call the heat-affected zone, or HAZ, it wants to expand. But it's constrained, see, by the colder, bulkier parent metal all around it. Imagine trying to expand in a really crowded room. You're kind of pushing against everyone else. This creates initial compressive stresses in that surrounding colder material.
Okay, yeah, that makes perfect sense. You're trying to push outwards, but the cold metal is pushing back.
Mm-hmm.
Then, as the weld pool solidifies and the whole area starts to cool down, that's where the real fun begins, right?
Precisely. As the weld metal and the HAZ cool, they naturally want to contract, shrink. But again, the surrounding colder parent metal resists this contraction. It's like trying to shrink in that same crowded room, but now everyone's holding you firmly in place. This resistance generates significant tensile stresses, essentially. The cooling material is pulling on the colder surrounding material.
Okay, here's where it gets really interesting, and frankly, a bit counterintuitive for me. These stresses, if they exceed the material's yield point, that's the critical stress level where the material stops just stretching elastically and actually starts to permanently change shape, right?
Exactly, the yield point.
Yeah. So if they exceed that, they cause permanent deformation. The material literally twists or bends. But then it might stop visibly distorting, yet those stresses don't just vanish, they get locked in. It's almost like the completed weld joint is perpetually trying to shrink, but it's being held in a stretched, kind of elastic state by the rest of the plate. Is that a fair way to picture it?
That's an excellent way to put it. Those are the residual stresses, the hidden, locked-in forces left in the joint after welding is all done. And they act in multiple directions: longitudinal, running parallel to the weld, and transverse, cutting across it. For very thick plates, you even get a through thickness component. It makes for a really complex internal force field.
Wow. Yeah. Okay.
And the sheer magnitude of these forces is driven by a surprising amount of volume change. Think about, say, CMN steel. From molten down to room temperature, the weld metal's volume shrinks by roughly 10% in total.
10%, that's huge.
It is. Imagine what a 10% volume reduction does to the forces locked inside a rigid structure. It means the very act of fusing metal is inherently creating this internal struggle, this relentless pull that must be managed. Otherwise, your structure could literally, well, tear itself apart or buckle under its own internal stress.
Right, that 10% figure really puts it into perspective. It's not just a minor effect.
Absolutely not. And it dictates the patterns of these stresses. Take transverse stresses, those perpendicular to the weld. Their magnitude depends quite a bit on how the parts are clamped or restrained. They're often relatively small in individual magnitude, yet they can lead to pretty substantial visible transverse distortion. You might see low magnitude tensile stress in the middle, then compressive stress out at the ends. And a key point here: the longer the weld, the higher that tensile residual stress can climb, sometimes right up to the material's yield strength.
Okay, so longer weld potentially mean higher locked-in tension across the weld.
Potentially, yes, until it hits that yield limit.
Yeah.
Now, longitudinal stresses along the weld, they're different. The weld itself and the immediately adjacent heat-affected zone are typically stressed right up to, or very near, their yield point in tension. As you move away from the weld into the parent plate, these tensile stresses gradually fall to zero, but then, even further out, you find a region of balancing compressive stress. It's a whole system trying to find equilibrium. The width of that main tensile stress band, that's a direct result of the heat input. Higher heat generally means a wider stressed zone. And here's the real kicker. Unless a weld undergoes very specific post-weld heat treatments, pretty much every single fusion weld you encounter, from a tiny bracket on your washing machine to a massive ship hull, contains residual stresses. They're just a universal truth of welding.
Wow. Okay, so we have these invisible, locked-in forces everywhere in welded structures. What does this actually mean for the strength and reliability of products in the real world? Why should someone, outside of an engineering lab truly care about this internal tug of war?
Well, this is where it really matters, where the rubber meets the road, so to speak. These stresses are generally considered detrimental for several key reasons, impacting both safety and functionality. First, and most visibly, they cause distortion. Structures literally become out of shape, warped, twisted. This can render them simply not fit for purpose. Imagine a bridge component that's warped by even a few millimeters. It just isn't going to fit precisely where it needs to go.
Right, assembly becomes a nightmare or impossible.
Exactly. Second, they can wreak havoc on dimensional stability. Say you need to machine a welded component to incredibly tight tolerances. If you start removing layers of metal near that weld joint, you're disturbing that existing delicate stress balance. This can cause further deformation or warping after machining. It makes holding critical dimensions incredibly difficult. Sometimes, post-weld stress relieving is the only way to guarantee you can achieve those tight tolerances reliably.
Okay, so it messes up precision work after the welding is done. What else?
Well, perhaps the most critical impact is that residual stresses can significantly enhance the risk of brittle fracture, especially at low temperatures. Think of a ship traversing icy waters. The combination of freezing temperatures and those pre-existing tensile residual stresses near a weld could, potentially, lead to a sudden catastrophic failure.
That sounds terrifying.
It is. And this is why engineers are so careful selecting materials and often mandate stress relieving for critical applications like pressure vessels. The risk of a catastrophic failure, like an explosion or structural collapse, is just too high to ignore. And finally, these stresses can also facilitate certain types of corrosion, particularly stress corrosion cracking in specific environments and metals. Again, stress relieving can be a key strategy to slow down or retard this sort of insidious attack.
It really sounds like welding, despite its incredible utility for joining things, inherently introduces this kind of Achilles heel. Designers aren't just sticking metal together, they're constantly performing this balancing act. Selecting materials, designing joints, specifying procedures, all to try and outmaneuver these inherent challenges. Okay, we've established that the root cause of all this distortion is that non-uniform heating and cooling cycle during welding, which leads to plastic deformation when stresses get too high. But how exactly does that manifest visually? What kinds of, twists and turns are we actually talking about seeing in a finished part?
Right, so the permanent deformation, the distortion, shows up in several main types. You get longitudinal shrinkage, where the whole thing contracts along the length of the weld itself. Then there's transverse shrinkage, where it pulls inward across the width of the weld. This often causes parallel parts to get closer together than you intended. Angular distortion is very common, particularly in things like single V butt welds. Because the contraction isn't uniform through the thickness, it causes the plates to rotate or cup upwards or downwards relative to each other.
Okay, shrinkage along the weld, shrinkage across the weld, and tilting or cupping.
Exactly. Then you get into some larger scale issues. Bowing can occur when the weld center isn't perfectly aligned with the neutral axis of the section, that imaginary line through the center where bending stresses are zero. This shrinkage force then acts like a lever, causing the entire member to curve, sort of like a banana. Similarly, dishing is often seen in large, stiffened plates like ship decks. The angular distortion from welding the stiffeners to the plate causes the plate sections between the stiffeners to dish inwards, almost like a shallow bowl. And finally, there's buckling. This happens mainly in thin plates when those long-range compressive residual stresses we mentioned earlier cause the plate to severely ripple or dish out of plane. It's like crumpling a piece of paper, but with steel.
Wow. Quite a variety of ways things can go wrong geometrically.
Yes, but they all stem from that same fundamental principle: the material trying to shrink unevenly as it cools. A simple way to think about it is that both transverse and longitudinal shrinkage pull the material inwards, while that uneven contraction through the thickness creates the angular rotation or distortion. And it's definitely worth noting that just increasing a fillet weld leg length, even slightly, say from 6 mm to 8 mm, doesn't just add a bit more metal, it can drastically increase the shrinkage and the resulting distortion.
Right, more weld means more shrinkage, generally speaking. So whether it's a tiny internal pull or a big visible curve, it all tracks back to that initial thermal battle. It stands to reason, then, that the factors influencing these residual stresses would also be the main things driving distortion, wouldn't they? What are the key levers engineers can pull?
You're absolutely right. Stresses and distortion are deeply interconnected. We can usually group the influencing factors into 5 crucial categories. First, material properties. Things like the coefficient of thermal expansion, basically, how much a material grows when heated, and its thermal conductivity, how quickly it moves heat away, are incredibly important. For instance, take stainless steel. It generally has a higher thermal expansion and a lower thermal conductivity compared to standard carbon steel. What does that mean?
It expands more and holds onto the heat longer.
Exactly. Which means it's notoriously prone to distortion during welding, significantly more than carbon steel, usually. Second factor, the amount of restraint. If you weld a component completely free, unrestrained, it will likely distort quite a bit as it cools, relieving some of those internal stresses. However, if you clamp it down really tightly, maybe using heavy jigs or strong backs, you can prevent a lot of that visible distortion. But here's the trade-off, and it raises an important point.
I think I see where this is going. Less visible distortion,
But you end up creating much higher levels of locked-in residual stress within the material itself, and that significantly increases the risk of cracking, especially if you're working with materials that are already sensitive to cracking. It's a constant balance.
Okay, restrain it and risk cracking, or let it move and deal with distortion. Tricky. What's next?
Third, joint design plays a huge role. For example, using double-sided joints in butt welds like a double V prep instead of a single V, or placing fillet welds symmetrically on both sides of a plate helps balance the thermal stresses. You're essentially pulling more evenly from both sides as it cools, which minimizes that angular distortion we talked about. Fourth is part fit-up. Having a uniform, consistent gap between the parts before welding leads to more predictable, uniform shrinkage. On the flip side, if you have excessive gaps, you have to fill them with more weld metal. And as we just discussed, more weld metal usually means more heat, more shrinkage, more distortion. Proper tack welding is also essential here to maintain that initial alignment and gap during the main weld.
Makes sense. Consistent input leads to consistent output. And the last category.
Finally, the welding procedure itself. Its main influence really comes down to heat input and weld deposition sequence. The general rule is to try and keep the total weld volume to a minimum for the required strength, and always try to balance those thermally induced stresses around the neutral axis of the component you're welding. Minimize the leverage effect.
That restraint trade-off is really fascinating. You're trading visible distortion for invisible, but potentially much more dangerous internal stress. So how do engineers actually fight this constant battle? It sounds like there's no single magic bullet. It's more of an intricate dance of different countermeasures. I understand we can sort of categorize the strategies into 3 main approaches: prevention through clever design, smart assembly techniques, and precise fabrication practices during welding.
That's a perfect summary. It's exactly that, a multi-pronged attack. Let's start with prevention by design. The ideal scenario, though not always possible, is the elimination of welding altogether. Can the component be formed from a single plate instead? Can a standard rolled section be used? That avoids the problem entirely. If welding is necessary, designers can look at using intermittent welds instead of continuous runs, assuming strength requirements allow it. That simply reduces the total amount of heat being pumped into the part.
Less heat, less problem. Simple enough.
Then, weld placement is crucial. The closer a weld is to that neutral axis of the fabrication. Remember, that imaginary line through the center where bending stresses are effectively zero, the less leverage the shrinkage forces have. Less leverage means less final distortion. The goal is often to balance welds on opposite sides of the neutral axis, or at least sequence the welding to alternate sides to constantly counteract the distortion. Thirdly, and this is absolutely key for both distortion control and economics, reducing weld metal volume. You want the weld cross-section to be as small as functionally possible while still meeting the design strength requirements.
Right. Minimize the sorts of the shrinkage.
Precisely. Certain processes like plasma or laser welding offer deep penetration with narrow welds, which helps. In more conventional welding, using double V joint preparations instead of single V can sometimes have the required weld metal volume. And here's a critical, often overlooked detail in practice: overwelding. Let's say the design calls for a 6 mm fillet weld, which provides sufficient strength. If the welder puts down an 8 mm fillet instead.
Just to be safe, maybe.
Maybe, but that 8 mm weld contains about 57% more weld metal than the 6 mm one. It adds nothing to the calculated design strength, but it adds significant cost in time and materials, and crucially, it significantly increases the distortion. It's truly a case where less is often more.
Wow, 57% more metal for no strength benefit, just more problems. That's a stark figure.
It really is. Next, there's a bit of a nuanced discussion around reducing the number of runs. Now, opinions can vary here depending on the joint type and situation, but often, particularly in a single-sided joint, making a single, larger weld deposit can result in less angular distortion than making multiple smaller runs to fill the same joint. However, those larger single deposits also tend to increase the overall longitudinal and transverse shrinkage, and they might increase the risk of elastic buckling in thinner materials. So it's another trade-off to consider.
Okay. Less angular twist, but maybe more shrinkage overall.
Potentially. Finally, under design, there's the technique of balanced welding. This is incredibly effective, especially for things like thick multi-pass butt welds. It involves carefully planning the welding sequence, which bead goes where and when, to continuously correct and prevent angular distortion from building up pass after pass. You're always trying to pull the structure back towards being straight and true. This principle can be applied to fillet joints, too. And if physically alternating sides isn't possible, sometimes designers use an asymmetrical joint preparation, deliberately putting more weld metal on the second side to actively counteract the distortion caused by the first side.
That's quite clever, using the weld itself to fight the distortion. So the design philosophy seems clear. Eliminate welding if you can, minimize the weld material when you do have to weld, place those welds intelligently on or near the neutral axis, and use balanced techniques. It's obvious that smart design here pays massive dividends way beyond just the drawing board.
Absolutely. Now, moving on to prevention by assembly techniques. These are the tactical steps you take on the shop floor before the welding torch is even lit. One method is presetting. Here, the parts are deliberately assembled slightly out of alignment, offset by a calculated amount in the opposite direction of the expected distortion. Then, they're often left relatively free to move during welding. The idea is that the welding distortion itself will pull them into their final, correct alignment.
So you use the distortion to your advantage.
Essentially, yes. The upside is it often doesn't require expensive clamping jigs and can result in lower final residual stress. The downside. Predicting that exact preset amount needed can be really difficult, often requiring trial and error or previous experience. Another approach is pre-bending, sometimes called pre-springing. This involves actively pre-stressing the assembly before welding, maybe using strong backs and wedges to create an internal counterforce that opposes the expected shrinkage during welding. When you release those wedges or clamps after welding is complete, the parts hopefully spring back into the desired alignment.
Okay, presetting lets it move into place. Pre-bending forces it back into place. What else?
Well, the most widely used technique by far remains simply the use of restraint. Parts are clamped down firmly, held tightly in position using jigs, fixtures, or temporary attachments like strongbacks to physically minimize movement during the welding cycle. But as we discussed earlier, there's that significant trade-off. While it effectively limits visible distortion,
It generates much higher residual stresses internally, increasing the risk of cracking.
precisely,
Yeah.
especially in materials that are already susceptible to cracking. It's worth noting that for on-site work, using wedged strongbacks is often preferred over fully welded strongbacks.
Yeah.
The wedges allow for some transverse shrinkage movement across the weld, which can help reduce that cracking risk compared to locking it down completely solid.
Right, a bit of compromise. So for assembly, you're either proactively predicting and using the distortion with presetting, counteracting it with pre-bending, or physically fighting it with restraint, but always keeping that potential for increased cracking risk in mind if you use heavy restraint.
That sums it up perfectly. Now let's talk about the third category. Prevention through fabrication techniques. These are the things you do during the welding process itself. Tack welding is incredibly important. It's not just about temporarily holding the pieces together. Good tack welds are essential for setting and maintaining the correct joint gap and providing that initial resistance to transverse shrinkage forces as the main weld goes in. Even the sequence of tack welding matters, whether you go straight through the joint, use a backstepping technique starting from one end, or start from the center and backstep outwards. It all helps maintain a uniform root gap, which is crucial for controlling distortion.
Interesting, even the tacks need a strategy.
Definitely. Another highly effective fabrication method is back-to-back assembly. You take two identical components, tack or clamp them securely back to back, and then weld them essentially simultaneously or in a balanced sequence. This brilliantly balances the welding shrinkage forces around the combined neutral axis of the assembly, making it incredibly effective for controlling angular distortion in things like T-beams or channels. Though you might need some careful handling, maybe stress relieving or using wedges when you eventually separate them.
That seems like a really smart way to use symmetry.
It is. We also sometimes use stiffening, particularly for long butt welds in thin plates which are prone to longitudinal bowing. You might temporarily attach longitudinal stiffeners, like flat bars or angle sections, parallel to the weld seam before welding. These act like a temporary backbone, providing rigidity and preventing the plate from bowing significantly along its length during and after welding. They're usually removed afterwards.
Okay, like a temporary exoskeleton makes sense. What about the welding process itself?
Yes, welding process selection plays a role. The general rules of thumb are usually to deposit the required weld metal as quickly as possible and, if practical, use the fewest number of runs. For manual welding, processes like MIG-MAG or GMAW often allow higher deposition rates than MMA, stick welding, so they might be preferred from a distortion perspective it's suitable. But really, mechanized or automated welding techniques often offer the greatest potential for distortion prevention simply because their consistency in travel speed, heat input, and bead placement makes prediction and techniques like presetting much more reliable and effective.
Consistency is key.
Absolutely. The welding technique employed by the welder is also paramount. Always keep welds to the minimum specified size, avoid that overwelding we talked about. Use balanced welding techniques around the neutral axis whenever possible. Sometimes this even involves having two welders working simultaneously on opposite sides of a joint, like double-sided fillets. Also, try to minimize the time lag between depositing successive runs in a multi-pass weld. Letting a pass get completely cold before the next one goes on can exacerbate distortion. It's known that angular distortion, in an unrestrained joint at least, is roughly proportional to the number of passes. More passes tend to mean more accumulated angular distortion.
Fewer, faster passes if possible. Got it. And
Finally, welding sequence and direction are critical, especially for longer welds. You should generally try to weld toward the free end of a joint, allowing the material some freedom to move as you progress. For very long welds, you don't typically just start at one end and weld continuously to the other. That maximizes heat buildup and shrinkage. Instead, short, strategically placed runs are often employed. Techniques like backstep welding are common. Here, you divide the weld into short segments, and you deposit each segment in the direction opposite to the overall progression of welding along the joint. Or there's skip welding, which involves depositing short, evenly spaced weld lengths along the joint, leaving gaps in between, and then coming back later to fill in those gaps, often in a sequence designed to balance the heat input. Both methods effectively distribute the heat and shrinkage more evenly, mitigating overall distortion.
Wow, that's a truly comprehensive toolbox of strategies during fabrication. From smart tacking sequences and back-to-back assembly to using temporary stiffeners, prioritizing faster, minimal run processes where feasible, and employing those clever welding sequences like backstep or skip welding. It really is a testament to how complex this simple act of joining metal actually becomes when you factor in these invisible forces. Now, despite all these incredibly well-thought-out preventive measures, design, assembly, fabrication, sometimes distortion still happens, doesn't it? It's like, I don't know, gravity, you can plan for it, but sometimes it still catches you off guard, or the constraints just don't allow perfect prevention. It seems really important to emphasize that prevention is always, always better, right? Because corrective techniques sound like they'd be costly, time-consuming, and probably demand significant skill. But when correction is necessary, what are the options then?
You're absolutely right. Prevention is always the preferred route. Correction is expensive and requires real expertise. But when distortion does occur and needs to be fixed, we generally turn to two main types of corrective techniques. First, there are mechanical techniques. This could, in some cases, involve careful hammering, though that carries risks of surface damage and undesirable work hardening of the material. More commonly, it involves pressing. Entire components or subassemblies might be straightened using a large hydraulic press. Now, the critical detail here, and it's counterintuitive again, is that you usually need to impose enough deformation in the press to actually overcorrect the distortion slightly.
Overcorrect. Why?
Because of elastic springback, when you release the pressure from the press, the material's natural elasticity will cause it to spring back partially. So you have to bend it past the target shape so that when it springs back, it lands right where you want it. For long components, this often involves a series of incremental pressings along the length. You can also use shaped formers or dies in the press to ensure you achieve perfect straightness or perhaps a required smooth curvature. Best practice for mechanical straightening usually involves planning that overcorrection with packing pieces, ensuring the component is adequately supported during pressing to prevent accidental buckling, using formals where needed, and crucially for safety, securely bolting any packing pieces to the press platen.
Okay, so mechanical means pressing past the target and letting it spring back. What's the alternative?
The second major category is thermal techniques, often referred to as flame straightening or local heating. This is really fascinating, almost like fighting fire with fire, or rather, fighting heat distortion with more heat. The basic principle is to strategically apply intense, localized heat to specific areas of the distorted component. This rapid heating causes the heated spot to try and expand, but it's constrained by the surrounding cold metal. This constraint generates very high compressive stresses locally, high enough to cause plastic deformation. The hot metal upsets or yields in compression. Then, when that heated spot cools down and tries to contract, because it was plastically compressed when hot, it ends up shrinking to a slightly smaller size than it was before heating. This localized shrinkage then generates tensile forces that pull the distorted component back towards its correct shape.
So you're creating tiny, powerful shrinking spots to pull the whole thing straight.
That's exactly the idea. The amount of straightening or shrinkage you achieve depends very precisely on the size, the number, the location, and importantly, the temperature reached in these heated zones. It often requires preliminary tests or significant experience to get it right for a new job. There are specific techniques used. Spot heating involves heating small, circular spots. It's typically used to remove buckling or waviness in thin sheets. You'd usually apply a pattern of symmetrical spots on the convex side, the bulge of the buckle. Line heating is often used to correct angular distortion, like in that cupped plate we discussed. You'd heat a narrow line along the weld, but critically, usually on the opposite side from the weld face, the side that needs pulling down or up. The shrinkage along that line pulls the flange flat. For larger, more complex fabrications, wedge-shaped heating might be necessary. Here, you heat a triangular or wedge pattern, aiming for a uniform temperature through the plate thickness if possible. You typically heat progressively from the wide base of the wedge towards the narrow apex. There are guidelines, for example. The wedge length might be about 2/3 of the plate width, and the width at the base about 1/6 of the length. This highly skilled technique can achieve significant straightening, maybe around 5 mm over a 3 m length, with one well-placed heated wedge.
That sounds incredibly precise. Are there risks?
Oh, absolutely. General precautions for all thermal techniques include avoiding overshrinking, which could make the distortion worse in the other direction, and crucially, avoiding metallurgical damage to the material. You have to control the temperature carefully. For common structural steels, you typically restrict the maximum temperature to around 650 degrees Celsius, which is about a dull red heat. Getting it too hot or cooling it too quickly afterwards could negatively affect the steel's properties. Best practice involves choosing the right pattern, spot, line, wedge, carefully restricting the heated area, controlling that peak temperature, and ensuring even heating within the target zone.
What an absolutely intricate dance between heat, material properties, structural mechanics, and human ingenuity. It's abundantly clear that welding is far, far more than just melting two pieces of metal together. It's this ongoing process of understanding and managing these powerful invisible forces that ultimately dictate the integrity, the safety, and the longevity of the final product.
Indeed. And if we connect this back to the bigger picture, I think understanding residual stresses and distortions truly transforms how we should view welded structures. They aren't just static, inert objects. They're really dynamic systems where these internal forces are constantly at play, constantly in equilibrium, even long after the structure is completed and put into service. It really highlights how crucial a deep, fundamental understanding of material behavior under thermal loads is for ensuring safety and performance out there in the real world. It's fundamentally about outsmarting the material's inherent tendency to twist and warp after being subjected to such intense localized heating.
Absolutely. A constant battle against physics, in a way. So the next time you look at the bridges you cross daily, the vehicles you ride in, or even, the everyday appliances in your home that might have welded components, maybe take a moment to think about how they're all silently relying on this delicate balance of unseen forces, this constant internal tug-of-war that engineers have worked so hard to manage. And perhaps it's worth asking, what hidden forces might be at play in your world, things seemingly insignificant on the surface, that might be causing long-term distortions or stresses you haven't fully considered? Thank you for joining us on this deep dive.